Good morning. We're starting to lose folks. You're the brave 20%. Okay, so I posted assignment number 2 yesterday. There's 4 assignments in the course. I think only the first 3 will be marked. The 4th will be just for you to study on your own before the final exam. So I posted assignment 2 yesterday. It's due in about 2.5 weeks, something like that, a few days before midterm, which is 3 weeks from today. Okay, so the date is in the course syllabus. Please make sure you don't skip that lecture. It will be here in this room. Somehow we're going to get 100 people in here. And it'll be 50 minutes long, so it won't be any longer than a normal lecture. Okay, 3 weeks from today, 8 in the morning. I'll talk about it a little bit more as we get a little bit closer as to where the cutoff will be in terms of content. It's going to include what we're still doing for at least the next week or so. Okay, so it'll be a written and paper exam, just like the good old days. And yeah, assignment number 2, you're still working on labs. I assume those are still going well. I talked to Logan yesterday. He said things were running smoothly as far as he could tell. I haven't heard any complaints from you folks, so I assume they're going well. Okay. All right, so let's finish off with the ARM processor today. Please keep reading in Appendix D as much as you can. I'm telling you the highlights. Obviously, there's a lot more to the ARM processor and the instruction set than we have time. And again, as I've said before, the aim in this course is not to make you experts in every last detail about ARM instructions, but the objective is that you are able to look at some relatively basic and straightforward ARM code and tell me what's going on in there, or to write some very basic ARM code to do some simple tasks, okay? And in assignment number 2, that's what you're going to be doing. In assignment number 2, there's a number of questions out of the back of Appendix D, which is talking about the ARM processor, and those problems have you write some basic code to do some simple, relatively simple things. Okay, so you'll get some practice in assignment 2. Yeah, and that's about it. Any questions, comments so far? Everything good, bad, ugly? Yes?
Can we, if we have time, go over question 210 on assignment 1?
Yes.
Yeah.
And I'm going to post the solutions too.
Yeah. Okay, I like when you go through them a bit too, instead of just the solutions.
Yeah, okay, so I can do that.
If there's time.
Yeah, there's 2 or 3 of your colleagues who, for various reasons, I have to give them a day or 2 of grace for assignment number 1, so I haven't posted these solutions just yet.
Okay.
I will on the weekend if I remember, or early next week. But yes, I can go over it quick in class too.
Cool.
Yeah. Just remind me in case
Okay.
it leaves my head. Anything else from anyone? Yes, sir.
What sort of difficulty should we be expecting for the website?
What sort of difficulty? Like the assignment questions.
So
And actually recognize that the midterm is going to be 15 minutes long. It's not just going to be coding. There's going to be some short answer questions. Because again, this course is not just about coding, right? It's about how our computer is set up. So I can't give you a coding problem that takes 2 hours to figure out, right? So they're going to be relatively short and straightforward. Okay, definitely not harder than any of the assignment questions. Yeah.
Will it be material from the textbook and the lecture slides, or just the lecture slides?
Textbook and lecture slides. Yeah. Yeah, I've said from the start that I really expect you to be reading in the textbook. The readings that I give you at the end of every lecture notes, it's not the whole textbook. I'm not asking you to read the whole textbook, but the sections that I put at the end of every lecture slide set. And those are the things that we're basically talking about, right? But yeah, I learned a long time ago to say yes. It covers all of that. Because if I ask a question and I didn't talk about it in detail in class, somebody complains. Any other comments, questions? Okay, and I'll talk more about the midterm as we get closer. We still got 3 weeks. Okay, let's finish off on the ARM then. Last day we looked at some of the instructions that we have available to us. TST, which is test, TEQ, test if equal, and CMP, which is compare. And these are instructions we can use to either see if a bit is set in a particular word, or to see if one word is equal to another word, or to see, just to compare two different data words to see if one is bigger than the other or one is less than the other. And what those instructions do is set specific bits, the condition or the status bits in the status register, right? So if you use CMP to compare two numbers, what it actually does is subtract those two numbers. If the result is 0, the Z bit, the 0 bit in that processor status register will be set equal to a 1, okay? And if that happens, that compare instruction, you now know, all you have to do is check to see if that Z bit is equal to 1. If it is, you know that that compare statement compared two values that were the same, because when you subtracted them, which is what the compare statement does, the result is a 0, sets the Z bit, and that's how the processor knows, those two things were equal. So typically what you do is you'll write one of those instructions, compare this number to that number, and then the next instruction will tell the processor what it should do based on that compare instruction before. So if the two values are equal, you set the Z, it sets the Z bit to 1, and then the next instruction will, okay, if they're equal, I want to do this, so I'm going to branch to this part of the code, or if they're not equal, I want to do something else, I branch to different instructions in the code, okay? Now and we're going to talk about branch instructions more in just a second, but unique to the ARM processor is you can actually make any instruction conditional on these flags or condition bits in the status register, okay? So, for instance, first look at this little bit of C code over here, okay? A simple if statement. If R0 is not equal to 5, I want to do this operation. R1 plus R0 minus R2 gets put into R1. Okay, obviously, if R0 is equal to 5, this gets skipped and we go on with whatever comes after that. So we can do that in ARM with these instructions. Okay, so we have a compare instruction. Compare what's in R0 with the immediate operand 5, so that's doing this. Okay, if R0 does contain the number 5, this, which is a subtraction really, will result in the Z bit being set equal to 1, okay? Well, the next instruction is a branch if equal instruction. And again, we're going to talk about branch instructions in a little bit more detail in a second, but this instruction simply says branch if whatever was done before resulted in equality, okay? If that's true, then we're going to branch to the instruction which is at the address bypass, okay? Which is here, bypass is a label for another instruction that comes later in the code. So if R0 has a 5 in it, this branch if equal is going to say, yes, they were equal, I'm going to branch, I'm going to skip these two instructions, go to bypass and do whatever's there, okay? Obviously, if R0 does not equal to 5, this branch does not execute because they weren't equal, and then it's going to add R0 to R1, put it in R1, add that, or subtract R2 from that. We're doing this over here, and put that into R1, so it does this. And then it keeps going with what comes after. Okay, so that's one way you can do it in ARM. You use a branch instruction. If these two numbers are equal, it's going to branch down here, it's going to skip these two lines. If they're not equal, it's not going to branch, it's going to do these two instructions, and then keep going with what's here. Or we can use this feature in the ARM instruction set which says we don't actually need that branch statement. We can make any instruction, including add and subtract instructions, conditional on what happened before. So this can be replaced with 3 instructions instead. Again, the first one is a compare. Compare the number 5 with what's in R0. And then we're going to have the add statement, or add instruction is exactly the same as this one, but it's got a suffix NE, which basically says add if not equal. Okay, so if the previous instruction did not require, if the previous instruction did not, where'd the word go, end up in equality, sorry, I'm missing the word, right, then it's going to do this add instruction, okay? And again, this instruction is going to set the Z bit to 1 if these two are equal, because the compare subtracts these two. If they're equal, that results in a 0, and the Z bit gets set equal to 1. This instruction, the NE, the processor is going to go, oh, I've got to check the Z bit. If the Z bit's equal to 1, that means they were equal, and I'm not going to do this. And it's going to go to the next instruction. Oh, NE, okay, I got to check the Z bit. It's still equal to 1, right? Because these two were equal, which resulted in a 0, set the Z bit to 1. Z bit's equal to 1, oh, that's equal, it's not equal, so I'm not going to do this instruction either. So it skips both of these instructions and goes on. But if these two were not equal, then their difference is going to be non-zero, meaning the Z bit, the 0 bit, gets set to 0. Okay, they're not equal to 0, so the Z bit is 0. So this gets not equal, checks the Z bit, 0. Yeah, that means that they weren't equal. So I'm going to do this instruction. Goes to the next one, checks the Z bit. Again, it's still 0. Oh, that means not equal. I'm going to do this instruction. So it just eliminates the need to have this branch state. And you can do this with pretty much every instruction in ARM, okay, by adding this suffix. And there's a number of different suffixes. We're going to look at those in the table coming up. Yep.
Does the first NE suffix have to be directly after the compare lines? Like, could I have just add and then subtract be subtract NE?
Yes, you could. Yes, you could. As long as, when you're using one of these suffixes, and you've got to compare instruction farther up, but there's instructions in between, as long as none of those instructions in between change the condition flags in the status register, you're okay.
Okay.
Right? Because they check those condition flags. These instructions with these suffixes check the condition flags. So you got to make sure as the programmer that you've done whatever you needed to do to make sure those condition flags are what they should be. So if you do the compare statement and then you do some other statement, which could, like you could have another, so for instance, if you did the compare and the add without the NE, and this add resulted in, okay, let's go back. The compare, let's say R0 and 5 are not equal. R0 does not contain 5 in it. Okay, then this difference will be non-zero and the Z bit will be set equal to 0. Okay? If the add was then executed and there's no NE, but that add resulted in a 0, then it's going to set the 0 bit to 1, right? So the compare set the Z bit to 0, the add without the NE, let's assume it sets the Z bit to 1. Well, now that might not be right for the subtracted instruction.
Wouldn't you have to store that bit in Z then?
No, the processor automatically does it.
Okay.
You don't store, you don't write values to those those Z bits and V bits and C bits. The processor does that automatically based on the instruction that just executed. So the safe thing to do generally is, if you've got an instruction, a conditional instruction like this, have the compare statement right before it, right? So that you know the condition flags are correct or properly set up for this conditional instruction that comes after. Okay, so obviously this results in smaller code, and that usually means it's faster. Okay, so that's something that's available. All right. When you write an instruction like this in your program, the assembler encodes this into a binary word of 32 bits. And it looks at this instruction and goes, oh, add not equals, okay, not equals, branch if equal. So let's talk about these suffixes. There's a number of different suffixes in this table, which is in Appendix D, I said that the 32 bits that an instruction is stored with, we call that the encoding of the instruction, right? Every instruction sits in 32 bits, a memory word of 32 bits. And part of those 32 bits, the upper 4 bits are what we call the condition field. So that's what we're talking about now. If you have a suffix, one of these conditional suffixes like equals or not equals or greater than or whatnot, it will set, when you encode that instruction, these 4 bits have to be set according to this, okay? That's what the assembler does, right? When you write, that means, if I can find it here, not equals, that means the first 4 bits of that 32 bits of that instruction are 0001. Okay, so there's a whole bunch of that you can use here. You know, there's a few that we use very commonly, the rest far less commonly. Equals, not equal to, no overflow or overflow, right? You might want to do something based on whether an overflow happened or not. Less than, greater than, equal to, less than, greater than, less than. Always is assumed, if you don't put a suffix, it's assumed that you mean do this, it's not a conditional statement. You always do this instruction, okay? Okay, and this is the condition test. So Z, C, N, V are all the condition flags in the status register. So these logical combinations here are what the processor tests. So for instance, we used what? Okay. So branch if equal, the processor just checks the Z bit. If the Z bit is equal to 1, that means equal, do it, okay? Yes, sir?
Why is there no unsigned higher or same or unsigned lower, just lower?
Why is there no unsigned lower or same?
Like, why is there's only unsigned higher and lower or same, but why is there no higher and higher or same or just lower?
I'm not sure I
Oh wait, no, never mind. I see them up there.
yeah, there's more down here. Does that help?
No, I see the carry set ones, those are what I'm talking about.
Okay. If you're looking in this table, this funny sign is actually the OR. I don't know why they use an up. That's really OR. This is exclusive OR. Don't worry about those. Once you start using these, like I said, there's just a few that we typically use, and I'll show you some examples. They start making sense. You don't really have to worry about that. Okay, but these are the ones that are all available to us, right? Z bit equal to 1, compare if equal. You can see what the branch if less than is right here. So it's the exclusive OR of the N, which is the negative bit, V with the overflow bit. Okay, so let's we're going to talk about branch in a second, and then we'll see more examples of it. Okay, so setting the condition code flags. Well, one of the ways we can do that are with those instructions test, TEQ, and compare. They always set the condition code flags based on whatever happened in that instruction. But our normal, regular instructions can also be set up to also do that. Okay, so arithmetic, logic, and move type of instructions, right? When you move a number from one register to another register, there's no reason that that instruction should update the condition codes, right? But you can force it to do so by adding the suffix S to the end of the instruction. So for instance, in add, if you add R1 to R2 and put the result in R0, that doesn't do anything to the condition code flags. But if you add an S to the end of that, then it will. Okay? So in this case, let's say we add R1 to R2 and the result was 0, that gets put into R0. In this one won't update the Z bit to be equal to 1, but this one will. Okay? So you don't necessarily just need, it's not just compare, test, and TEQ, those instructions that will set the condition code flags, and then you can branch or do other conditional things after that. Any instruction can be forced to update those condition code flags based on what happens in the instruction. Okay, so that's the suffix S. And like I said, compare, test, and TEQ, they don't need the suffix S, they always update those condition code flags based on what they're doing. Okay, so that's another thing you should be aware of. So you can take any instruction and make it conditional by adding that suffix at the end, like NE for not equal, and you can make any instruction update the condition code flag so that subsequent instructions can be conditional based on what happened by using this S suffix, okay? Without S, this is not going to update the condition code flags. Okay, any questions about that? Okay, so let's this table. Look at some, another example, okay? So let's look at this C code here, right? If A is equal to B and C is equal to D, we want to increment the variable E. Okay, so we can do that like this. So the first instruction is we're going to compare, let's say R0 and R1. Here, I'll write it up here. R0 is this one, R1 is this one, R2 is that one, and R3 is that one. Okay, so the first thing we're going to do is we're going to compare A to B using the CMP, the compare statement. So again, this is going to subtract these two values to see if they're equal. Because if you subtract these and it results in a 0, you know they're equal. If the result is non-zero, you know they're not equal. And it's the Z bit that tells us that. So that we do this comparison, okay? Now we're going to compare if equal. So we're making the compare statement conditional on what happened before it. Okay, this EQ suffix makes this statement conditional, and it's going to check the Z bit. So if the Z bit has been set equal to 1, that means some previous instruction resulted in a 0. That previous instruction was this compare, right? And because the compare subtract these two, if the result is a 0, that means they're equal. So the compare if equal means I'm only going to do this second instruction if the Z bit has been set equal to 1. And this previous instruction did that if R0 and R1 are in fact equal. Okay? And that's what we want to do. If we go back to the C code, the only reason to see if C is equal to D is if A in fact is equal to B. Right? If you took 177 with me, I might have told you about something called shortcutting. In an AND statement like this, the compiler doesn't even bother to look at this. If this is false, there's no reason to look at this, right? Because you're ANDing false ANDed with anything is false. So if the computer is going to do this comparison first, if these are not equal, it doesn't even do this. Same thing here. If this R0 and R1 are not equal, it doesn't even bother comparing R2 to R3. Same thing is happening in the assembler code, okay? But if A and B are equal, well then the Z bit's going to be set equal to 1. And if you go back, so we're going to compare if equal. If the Z bit's equal to 1, then we're going to do this comparison. We're going to check R2 and R3. And this is going to subtract these two. And again, update the Z bit in the processor status register. And then the third is also conditional. It's conditional on equal means it's going to check the Z bit. So if this one resulted in a Z bit being set equal to 1, which means yes, R2 minus R3 is equal to 0, which means they're equal, then it's going to do this addition, and it's going to add 1 to E, which is R4. Okay? So our code starts being a lot more efficient, a lot shorter, using these conditional suffixes at the end. Okay? Any questions about that 3 lines? Yep.
How would you implement an OR comparison instead of an AND comparison?
How would you do an OR? Good question. Anybody got an idea? Well, one way you could do is with a branch. check the first one, right pardon me, after this one. Because if this is true, we don't even have to bother doing this, right? So the second statement could be branch if equal, BEQ. And we would branch over this second one. That's the fastest. There's probably a way to do it without branch too, but that's the first thing that comes to my mind.
Branch over as in you would have,
The second one here would be a branch,
yeah.
which would skip the second statement if it was true.
Okay.
All right. Okay, table. Here's another one. Here's the C code. If R0 is less than 5, then we want to call some subroutine or a function. If it's C, sub 1. Else, call a different function, sub 2. Okay, we're going to talk about subroutines in a lecture or two down the road. So this can be implemented like this. Again, we're comparing two numbers. We're comparing the register R0 with the value 5, so we're going to use a compare instruction to do that. Again, it subtracts these two. It forms a difference between these two. If the difference is 0, you know they're equal. If the difference is not 0, you know they're not equal. If R0 minus 5 results in a positive value, well then you know R0 is greater than 5. If R0 minus 5 results in a negative value, you know that R0 is less than 5. Okay? So we're going to compare, and then we're going to, BL is branch and link, which is the branch instruction that we use when we're branching to a subroutine. We're going to talk about that in a while. Okay, this is just going to branch to a subroutine. Sub 1 is just a label for a memory address. It's going to branch to some other address and do the instructions there. Okay? So branch LT is less than. Okay? So if R0 is less than the number 5, well that obviously means that this was a negative value, R0 minus 5, right? So R0 less than 5, we're going to call sub 1. So branch if less than. Okay, and if you go back to, but again, you don't have to worry about that. Once you've seen a few examples, you get how to use them, right? So it's basically R0 minus I5. Branch if less than means R0 is less than 5. Yes, it's going to branch to this address and keep going. If not, it's going to do the next one, branch if greater than equal to, which is this case, the else case. It's going to branch to that address, sub 2, and keep going with the instructions there. Okay? Okay, and let's talk about branch instructions. Branch instructions contain assign 2's complement 24-bit offset that is shifted by 2 to form a word offset. Great. This offset, which can only be a maximum of plus or minus 32 megabytes, is added to the PC, the program counter. The program counter always holds the address of the next instruction to be executed. So when a branch instruction is executed, this offset is added to the program counter, and then the program counter is updated with this new address so that once the branch instruction is finished executing, the next instruction is not going to be the one right after the branch, it's going to be the one at the address of the next branch plus the offset. So it's just a way to branch to a different place in our code, okay? So we have two different branches. We have just the plain old-fashioned branch, okay, which means if this is true, I'm going to branch down here. If this is not true, I'm going to keep going with the next instruction, okay? And we can make them conditional, like we've seen, branch if equal, branch if less than, branch if greater than equal to a label which stands for a memory address. This is the address of the instruction you want to go to if this branch condition is true, okay? Or if there's no condition, it just means always branch, right? When you get to that point, go here. BL is branch and link. This is for subroutines that we're going to talk about in a few minutes. Okay, so example conditions are equal, not equal, greater than or equal to, or always, like I've said. Okay, in addition to setting the program counter, okay, so what's the difference between B and BL? Branch is just go to this part of the code and just keep going what's there. A subroutine is like a function in C, okay? And you know that with a function in C, you have your main program, you call the function, what happens? computer execution goes to that function, does what's there, and when it's done, it returns back to the main program and keeps going with what came after the function call in the main program, right? Well, that's what we use the branch and link instruction for. In assembly, we have to, when you hit a branch and link, the processor has to remember, okay, I'm gonna go to somewhere else, I'm gonna branch somewhere else in the code, do what's there, but when I get to the end of this subroutine, I need to return back to the main program and keep going with the next instruction. So the processor has to remember, where do I go back to? Okay, and we call that the link register. So one of our general purpose registers in the ARM processor, R14, is reserved for this. So the branch and link is gonna do this automatically. It's gonna branch, you know, if this condition is true, if there is a condition, it's gonna branch to that subroutine, and when it does that, it's going to save the address of the next instruction after the branch in the link register, so that when the processor is done the subroutine, it goes, oh, where do I go next? Ah, this was a branch and link. I'm gonna go back to the link register, and that tells me where to go back to in my main program. We're gonna talk about that more in a second. So, very simple branch instruction example. I forget what this is doing. We're adding up numbers again. So load register R1 with what is at memory address N. Okay, so memory address N is holding the number of numbers, okay, that we're gonna add up. Load register R2, equal sign again, tells the assembler num1, which is a label for an address. We're gonna load an address into R2. That's how we do it, okay? So now R2 holds the address of the first number in our list. R1 holds the number of numbers in our list. We're gonna move the immediate value 0 into R0, so R0 is gonna be our running sum. And now we're going to have load register R3 with, this is the pre-index, no, this is the post-index mode, okay? So we're gonna take what is in R2, which is the address num1, and we're gonna get whatever's at num1, which is the first number in our list, and we're gonna put it into register R3. And then we're gonna update R2 with num1 plus 4. Then we're going to add this number, R3, into R0, which has 0 in it, put the result in R0, so now R0 has the first number in our list. Then we're going to subtract, and S means update the condition codes in the processor status register. We're going to subtract 1 from R1. R1 is our counter, keeping track of how many numbers. We're going to subtract 1 from that and put it back into R1. And the S is going to update the condition flags based on this subtraction. Okay? Then we're going to branch if greater than to loop back up here. If we haven't reached the end of our list of numbers, we want to go back, get the next number, add it to the running sum, and just keep doing that. Okay? So this branch greater than is going to look at what happened before, and what happened before was we subtracted 1 from R1. So if R1 was greater than the number 1, if whatever was in R1 was greater than the number 1, this is going to be true and it's going to branch. Okay? And so it would be a really good idea if sometimes this Thanksgiving weekend, you just do this for yourself. And don't make the list long. 3 numbers would do. Okay? Just pretend n, small n is, or what's stored at n is 3, and I've got 3 numbers I'm going to add up. Go through this yourself, keeping track of what's in every register, okay? And you'll see that you don't want to branch here anymore when R1 has 1 in it, okay? Because the first time through, R1's going to have 3 in it, if it's 3 numbers we're adding. Second time, it's going to have 2 in it. Okay, now it goes back. Now it has 1 in it. I've added my 3 numbers. I don't want to branch and go back and add a 4th number, which I don't have. Okay, so the way to remember what this branch is doing is branch greater than, branch if R1 is greater than 1 is how it actually works. Okay, again, go through this yourself. Good practice for the midterm. Okay, so obviously when we've gone through the last number, this R1 will be equal to 1. We don't want to branch anymore. So this will not be true. Greater than, R1 is no longer greater than the number 1. So this will be false, and we're going to go, and then we're just going to store that number in memory. Okay, so please, you know, if you want to practice for the midterm, go through these examples yourself. Write down R0, R1, R2. Do the instructions one at a time, and make sure you can, you know, keep track of what's going on and that it all makes sense to you. And if you have any questions, let me know. Okay? Okay, so that's a simple branch instruction. So keep reading, new reading assignment 2.6. Okay? And even in Appendix D, I'm not asking you to read absolutely everything. I'm giving you exactly what you should be reading. Okay? All right, let's keep going. Next slides, lecture 8 slides, stacks and queues. This is relatively short and straightforward. We've got two types of data structures that we commonly use in programming, not just assembly language, but pretty much any type of programming. We didn't talk about them in 177. Stacks is very much, no, I won't say that, doesn't matter. Okay, it's a type of data structure, and the data structure is just how do we keep some numbers in memory so that we can use them, okay? It's a data structure with the restriction that elements can only be added and removed from the end of the list, top of the stack, also known as last in, first out, a LIFO stack, okay? So memory, we just always visualize memory as a sequential memory words, okay, with address 0 up to a large number. Okay, we've seen that a million times in this course already. Well, a data structure is just some block of memory words that are reserved for this data structure. One type of data structure is a stack. And a stack is basically a stack of numbers in memory, okay? And if my stack is empty and I want to push a number on the stack, that's the terminology we use, push and pop. When you push something onto a stack, you put it on the stack. When you pop it off, what did I say? Push and pull? It's push and pop. When you want to take a number off the stack, you pop it off the stack, okay? And it's like stacking paper, right? I put one piece of paper down, I put the next one on top, the next one on top, the next one on top, and I build my stack, okay? Now, once I've built a stack of papers, I can't just go and take one out of the middle, okay? I got to take the top one off first. And then I can take the next one, and then the next one, and then the next one, right? So the first piece of paper I put in my stack is the last one to come out, okay? Which is why we call last in, first out. Oh, that's the other way around. The last one that I put on my stack is the first one to come off the stack, okay? You can't go and grab papers from the bottom or anywhere in the middle of the stack. You can only take them off the top. Same thing with here. Generally, it doesn't have to be, but generally, the bottom of my stack is the higher order, the higher address, and stacks grow towards lower memory addresses. Doesn't have to be that way, but typically that's how it's done, okay? So if I have an empty stack, and I put something on the stack, it's going to go here. And then the next number I push onto my stack is going to be here. And then the next one here, 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 okay? In order to keep track of our stack, because the stack can grow and it can ungrow or get smaller, okay? We have to keep track of where the top of the stack is. The bottom of the stack is always here. But the top of the stack grows up as we push more numbers onto the stack, and then it goes down as we pop numbers off of the stack. So we got to keep track of where's the top of the stack right now. And we use a register to do that called the stack pointer. Okay, so the stack pointer is one of our general purpose registers in the ARM processor, and it always has the memory address of the top of my stack in it. Okay, so when I push something onto the stack, I have to update the stack pointer to now point to that new number that I pushed on the stack. When I push another number onto the stack, I update my pointer to point to that one. It's always pointing at the top number in my stack. When I pop a number off the stack, if I take the negative 28 off of my stack pointer now has to be updated so that it's pointing at my new top of stack. So it's pretty simple and straightforward. Okay, you build up, you grow it down as you take numbers off. Okay? So again, you can't take a number out of the middle of the stack. You have to remove it always from the top of the stack. So that's a stack, okay? So code to do it, this is just generic code again. This is not ARM processor. We're back in chapter 2, I think. Yeah, 2.6 was the reading assignment. So this is back to chapter 2. So this is just generic assembly code again, okay? So pushing means putting a number on the stack. Okay, well, the first thing I do, so if my stack looks like this, it's not telling you what the number is. Oh, new item, 19. Okay, so if before this code happens, my stack, the top of the stack is right here. Okay? Now I want to push the number 19 onto my stack. So what am I going to do? I'm going to first update my stack pointer. Okay? It grows towards lower memory address, so I have to subtract 4, 32 bits per memory word, 4 bytes. I have to subtract 4 from what's in the current stack pointer. Current stack pointer is this address. I subtract 4 from it. Now the stack pointer is pointing at this memory address. And now I can use that to store my number, RJ, which has 19 in it, at that new address. Or if my instruction set has the auto decrement feature, then I can just do it in one instruction, right? This is going to say, okay, take the address of that SP has in it, which is currently this address, subtract 1 memory word from it, 4, update SP with that, and put the value in RJ at that address. It's doing the exact same thing as these 2 instructions. Okay, popping means taking a number off of the stack. Okay, so now I want to take 19 is the only, once my stack looks like this, 19 is the only number I can take off of the stack. That's not the same thing as accessing a memory in stack. I can access any of these numbers that I want. But when I access it, that means I just might want to use the number 739. I might want to read this number at this point in the stack and use it in some calculation. That's not taking the number off of the stack. Okay, I can always access a number in the stack, but I can only pop off the top one. I can only get, and pop means get rid of. I want to get it out of the stack. I don't need it anymore, for instance. Okay, I can only get rid of the 19. So what am I going to do? Well, I'm going to load register RJ with what's at memory address that the stack pointer is pointing to. So I'm putting the, oh, okay, let's take 19 off. So no, it's 19. We're popping off negative 28, sorry. The item is negative 28. So stack pointer, when this code starts, the stack pointer is pointing at the top of the stack, okay? I'm going to take whatever number stack pointer is pointing to, which is negative 28, and I'm going to put it into RJ. And now maybe I do something with it, okay? But I don't need it in my stack anymore. So all I got to do now is add 4 to the address in stack pointer, and now stack pointer points to this number. This is my new top of stack, okay? Did I delete this value out of this memory address, memory location? No, I didn't, okay? This just loads it. Remember, a load just takes a copy of this and puts it in register RJ. Doesn't erase it out of memory. It's still there. But now my stack pointer, by pointing to the top of the stack here now, this number is not in my stack anymore. If I now push a new number onto my stack, it's going to write over this number, right? But until I do that, that number is still there. It's just now my stack pointer's here, so now it's negative 28 is no longer part of the stack. Or I can use the auto increment feature to do the same thing, right? I want my stack pointer's pointing at negative 28. I want to take it and pop it and put it into RJ, and then I want to add 4, so my stack pointer points to the next memory address to my new top of stack. And this is why the auto decrement always happens first, and the auto increment always happens after. Most instruction sets don't have an auto decrement where the negative is after, or an auto increment where the addition is before, because they're primarily used for manipulating the stack pointer, and we always want to decrement the stack pointer first, or increment it after. Okay, so that's a stack. Yes, sir.
So what's the point of a stack?
We're holding numbers in there and we know where they are. A data structure is just and you're gonna see when we get to subroutines, because in subroutines, we're going to store a bunch of stuff that the subroutine needs on the stack. So once it's on the stack, now the processor can go to the subroutine, and those instructions, oh, we need to know some numbers. It's like passing parameters to a function in C. The way we do that in assembly is we put those numbers on the stack, and then the subroutine goes and gets them off of the stack. It's just we know where those numbers are in memory. Okay? You can only pop things off until you get to the bottom of the stack. Okay. All right, popping and pushing safely. Need to make sure we don't pop too many items. Right, obvious. All right, the second data structure we want to look at is queues. We're not going to use queues very much at all in this course, but you should know what they are, okay? A queue is another data structure like a stack. It's just a block of memory locations, but it's a first in, first out, okay? So a queue is like what you line up in at the bank. You don't line up in a stack at the bank, right? If you lined up in a stack at the bank, that means the last person to walk in the door and get in line would be the first person to be serviced, right? Everybody would cry bloody murder. What you do is line up in a queue, like the English say. That's why the English don't call it a lineup, they call it a queue. Because if you're the first one into the bank, you're at the head of the line, you're the first one to get out of that line and be serviced by a teller, right? So that's exactly what a queue is. It's like a bank lineup, or now at the grocery stores, right? First in, first out. So we add data to the back of the queue. When you walk into the bank, where do you go? You go to the back of the line, right? And to get out of the queue, you get out at the front of the line. You work your way up and you get out at the front. That's exactly what we have here. So typically, the back of the queue, again, is a high address. It doesn't have to be, but that's typically how it works. So if we have a block of memory from address 1500 to 2000, this would be our queue, okay? So when we add data to our queue, we would add it to the back of the queue, which is at a higher address, okay? And we would take data off the front of the queue. So obviously, as data is taken off the front of the queue, everybody moves up, right? Until finally, the last one in is the last one out, or the first one in is the first one out. Okay, to keep track of a queue, we need 2 pointers. Stack, we only needed 1 pointer because the bottom of the stack is always at a certain address, it never changes, and the top of the stack goes up and down as we put numbers on and take numbers off. With a queue, we need to know where's the last one, or the last person who just came in the queue, where's the first one at the head of the line. So we need an in pointer and an out pointer with a queue, okay? The in pointer contains the address where the next item will be added to the back of the queue. Okay, so that means the last number to go into our queue currently sits here, and we're ready for the next number to come into the queue here. Okay, the out pointer contains the address where the next item will be removed from the front of the queue. So the number, this is the guy at the head of the line at the bank, okay? He's here. Here's the guy at the end of the line. Next person to walk out the door goes here. Okay, so we need 2 pointers. Well, obviously, this becomes a problem because both ends of the queue actually start moving as people come and go, okay? Or as data comes and goes, right? As I add people into the queue, this pointer is going to go down, right? It says it here. Both ends of the queue move to higher addresses as data is added and removed, right? So if these are here's the in pointer and out pointer. When a new person comes in pointer's got to do this, goes to a higher address. When somebody leaves off the top, out pointer also goes to a higher address, right? They both go down. So my queue is going to start migrating through memory as data comes and goes, okay? Well, that obviously becomes a problem. You don't want your queue to go all the way through memory because what are you going to do? You're going to overwrite other stuff in memory, right? You can't just let your queue go all the way through memory. So how do we limit it? and we'll end with this. Move all the items in the queue down one address whenever an item is removed from the queue. So the out pointer will remain pointing at address 1500. So move all the items in the queue down one address whenever an item is removed from the queue. So we just move everybody gets moved down one, okay? Because we don't want to keep migrating through. So the out pointer will remain pointing at address 1500. The in pointer will move to a higher address as items are added to the back of the queue. So this is slow because every time you take a number off the queue, you got to change everybody's memory address. You got to move them all down one, okay? Which is obviously not very good. We'll talk about this more on weapon solution, that's better. So have a great long weekend. We'll see you next Wednesday. Wednesday, because there's